Hey guys, my name's Tanner Williford. Today we're going to be talking about power and electric circuits. Most of the information that we'll be discussing today can be found in the College Stacks College Physics book in chapter 20.4. So as you can see here, we're going to start by talking about what power is conceptually. Next, we'll try to apply this concept of power to an electric circuit. We'll then go on to cover some of the equations related to this concept, how we can plug in certain values and manipulate the equation based on what we're trying to solve for. And then we'll finish by taking everything we discuss and applying it to solve a practice problem just to make sure that we understand the material and can utilize what we talk about today. All right, so let's start off by talking about what we should know at this point about power, and that is that power is the rate at which work is done. And if we try to put this into an equation, we'll see that power represented by P equals work over time. So when I'm trying to conceptually understand what power is, I try to think of myself or imagine myself running up these stairs and then asking myself, what would require me to use more power? Would it be me running up the stairs at a slower pace or a faster pace? And when you work through both of these, you see that the work doesn't change, but our time interval does. So if our time is going up and we're running slower, our power is actually going to decrease. And on the opposite end of that, if we go up the stairs a little bit faster, we'll see that our time will actually decrease. And in turn, our power will actually go up, which means that as we increase in our speed running up these stairs, it will require us to use more power. So if we take this example and we try to kind of reimagine the way that we see or define power, we'll realize that we can actually define power as the rate of energy use or energy conversion, and understanding that in an equation, which is also one that we should be familiar with at this point, would be P equals WT, or a change in potential energy over time. All right, so now let's take this information and see if we can apply it to an electric circuit. So we know that power is the rate of energy use or energy conversion, and that power equals a change in potential energy over time. You'll see here that you're able to rearrange that equation and derive the equation P equals I times V, where I is current and V is volts. So since we kind of redefined this way to mathematically come to power when applying it to an electric circuit, it might be a good idea at this point to also come up with a new definition that applies more to an electric circuit. When we do that, we'll see that what we come to is a power is the rate that energy is supplied by a source or dissipated by a device. So to kind of understand this definition a little bit better, what we can do is understand it in terms of this. So the square looking thing here is a electric circuit or current. This negative and positive charge is actually going to be our voltage, and we can imagine that to just be something like a battery. These squiggly lines over here is actually going to be a resistor, and we can imagine that for the purpose of this video to be a light bulb. So when it says that power is the rate that energy is supplied by a source, the source that we're referring to for the purpose of this video is going to be this battery here, which is supplying the voltage. And then when it says or dissipated by a device, that is going to play and come into an effect over here, because when we talk about dissipate, what we're saying is that this energy is being converted into a different type of energy. And since we are allowing the resistor for the purpose of this video to be a light bulb, we can imagine that the current and the voltage runs through, hits this resistor, the light turns on and converts this energy into heat. It's also good to understand what the units are for power. So power, or P, is always going to be represented in terms of watts or W. And when we break this down, it is actually going to be joules over seconds. All right, so hopefully at this point it kind of makes sense how power can be thought of in terms of an electric circuit, and how we derive the equation P equals I times V. What we can do at this point is actually also derive a few other equations by breaking down the I and the V. If you want to pause this and kind of look at how I did that, feel free to do so, and you'll see that there are actually a few equations that we can use based on the information that we are given in a type of question. So when we break these down, there is one important thing to note, and that is that this original equation that we came up with to define P in terms of an electric circuit, which is P equals I times V, is always going to be valid for electric circuits, always. The only reason that we would use this equation or this equation is when resistors are involved. I think that we're ready for a practice problem to really put this knowledge and information into practice and see if we're able to solve problems and apply what we've been talking about for the last few minutes. So this question here says, when connected to a 6-volt battery, a certain resistor dissipates energy with a power of 50 watts. What is the power when the resistor is connected to a 12-volt battery? So if you want to pause the video real quick and read over that a few times to kind of understand it a little bit better, feel free to do so. When you come back to the video, you'll realize that in the second sentence there, it's saying, what is the power when the resistor is connected to a 12-volt battery? And what you'll realize is that we don't have the value for the resistor. So what we have to do is break this problem into 2 steps. And you'll see that I've taken the liberty to kind of draw out this first step for us. So if you want to go back to the equations that we just went over and figure out which one to use, you'll soon realize that this is the best equation to use because we are given our volts and we are given power. And what we can solve for is our resistor value. So if we take this equation and we rearrange it to solve for R, what we get is this here. And then if we plug the values in, we get 6 V raised to the second power over 50 watts. And if you plug that into your calculator real quick, what you'll get, or what you should get, is 0.72 ohms. So this sign right here is always going to be the units for a resistor. And it stands for ohms, which is OHMS. So now that we have our ohms, we can go ahead and try to solve the second part of this question, which is solving for power. So let's go ahead and do that. So when we use that same equation, P equals V to the second power over R, we can plug in for our resistor value, which we found to be 0.72, and the voltage, which is actually going to be 12 volts now, into this equation, and what we'll get is 200 watts. So I kind of drew this electric circuit here, so while you're doing this question, you can kind of conceptually think about what's going on. In summary, when talking about power in an electric circuit, we can take power as being the rate of work done and rearranging that to be defined as the rate of energy supplied by a source or the rate of energy dissipated by a device. When talking about power in an electric circuit, it's always going to be represented in units of watts, which can be broken down into joules per second. And I have also included some of the main equations that we need to know when solving for power or when given power and solving for a different value.